opportunity to show our current results. So I am Veerendra from Solid State Physics Division of Bhabha Atomic Center, and I will talk about the physics of the action mechanism of antimicrobial peptides. So prior to begin, this is the current research activity of our group. So I am working in the area of membrane biophysics, where I am talking about we are investigating the structures and the dynamical behavior and the phase transitions of the lipid membrane and the interactions of antimicrobial peptides and drugs and stimulants with the lipid bilayer. Another area is the soft matter, where I am investigating the dynamical landscape of various self-assembled aggregates like metallosomes, bicontinuous microemulsion, micelles, lithium-based deep active solvents, where we are looking the role of the dynamical heterogeneity on the transport mechanism of the deep active solvents, and last, energy materials, where we are working on the hybrid organic and inorganic peroxides to look at the reorientational motion of these cations and how they play the important role in the functionality of these peroxides. So this is the brief introduction of my talk. I will give a brief introduction about the lipid membrane and antimicrobial peptides and what is the antibiotic resistance. Then we use various methods and the computer simulation, but I will focus mainly on the Neutron scattering, and then I will discuss brief our current results, and then I will conclude. So antibiotic resistance, as name prevails, the bacteria which earlier susceptible to the antibiotics now mutate and become resistant to antibiotics. That we call the drug resistant bacteria or superbugs or multi-drug resistant bacteria like MDR2V. And this process is the natural process, but by misuse of the antibiotic, we are accelerating this process. And it's severe threats to the public health, like if the current studies show around 7 lakh deaths per year is happening worldwide because of the antibiotic resistance. We can estimate, and it's predicted that more than 10 million deaths per year by 2050 if we don't control the misuse of antibiotics. So WHO organized the World Antibiotic Awareness Week, and we should care the antibiotic with care. And you will be surprised to know that India has the highest antibiotic consumptions, and we need to strengthen the regulation of the distribution as well as the consumption of the antibiotic. And now we do see in the media also, like the IMA advice against indiscriminate use of antibiotics. So there is an arms race between the antibiotics and bacteria, and we need to develop a novel alternative which are more resistant for the antibiotic resistance. So antimicrobial peptides are the most promising candidates because they are the part of our innate immune system which conserve their efficiency over millions of years. They are small polypeptides which are about 10 to 100 amino acids, and they do have a broad spectrum of their activity for both gram-positive and gram-negative bacteria. They quickly act on the pathogens. So all living organisms have the antimicrobial peptides, and I selected 3 antimicrobial peptides from bee venom, from Australian frog, and from human to do our study. And this is the traditional action mechanism, that these peptides don't need any receptors. They directly interact with the lipid membrane, the cell membranes, and generally in the solutions they are the random coil conformation, but when they come in the contact with the lipid bilayer, they change their secondary structures and they form the alpha helical or beta sheets, and they create the pore. And there are different pore formation mechanism. I won't go into the details like a toroidal pore, barrage or carpet model, but this is the traditional mechanism by which the lipids creates the pore. But the recent observation, we have mentioned in this review article, that the recent observation have suggested that there are other action mechanisms by which these peptides disrupt the lipid membrane. They won't create the pore because this pore formation happens only at high concentration. So even at a low concentration, they disrupt the lipid membrane, their structure and the dynamics, which may affect the stability of the cells. So prior beginning, I would like to discuss about what is the cell membrane or the lipid membrane. So I have taken a very simple example of the eukaryotic cell. And the cell membrane is nothing, it's a physical boundary between the cells and its cell cytoplasm and its external environment. And it's a very heterogeneous mixture of the lipids, proteins and carbohydrates. And they play a very important role in many physiological functionality like cell signaling or selective permeability. So they should be elastic enough to contain all organelles within the cells, but they should be fluid enough to allow the movements of the lipids and the proteins for their functionality. So they should maintain a very balanced fluidity. If you alter this balanced fluidity, like if membrane become more fluidic, it start to leak out. So it will affect the stability of the cells. Or if it's more elastic, it won't allow to the movement of the lipids and protein, that will affect the functionality of membrane protein. So the cell membrane should have a very balanced fluidity for their functionality. If any additive, any change the balance fluidity, it may affect the stability of the cells. That's the prime concept we have taken care. And if you go about, because we are a physicist, so we don't work on the real cell membrane, so we work on the model system. And if you take about the fundamental building block of the cell membrane is the lipids, which is nothing, it's antiphilic molecule. And this bilayer typically around 5 nanometers, we can do easily by the scattering technique. We can see the structures, and they do have a very different phase transitions. And as a physicist point of view, again the phase transition is very important for us. So they form a very highly ordered, like a crystals in the condensed matter, and they another end they have a highly fluidic structure like a disordered states. In between they do have like a gel-like structure in which the tails are highly ordered, but the heads are highly disordered. And they may form different polymorphs like interdigitated one, the tilted one, and the periodic ripples. And this phase behavior you can tune by the temperature, molecular structure, composition, and the concentration of the lipids. And this is the another our area that how we investigate the different phase transition in the lipid membrane system. The another interesting point of view, they have a huge dynamic landscape. You can see the motion occurring from the few hours like a flip-flop motion to sub-picoseconds motions, like laterally the lipids are diffusing within the leaflet. This is a flip-flop. They doing the internal motion. Whole bilayer are undergoing the bending fluctuation as well as the thickness fluctuation. So we are we are a lot of interest to investigate this dynamical phenomena. So this is our strategy. We want to study the interplay between the lipid membrane and the antimicrobial peptides. So what we do, we investigate the structure, dynamics, and the phase behavior of lipid membrane in absence and presence of antimicrobial peptides using various techniques. We do investigate the structure of antimicrobial peptide by circular dichorism and the thermodynamic interaction between the peptides and lipid membrane by the calorimetry and the isotherm. So just for the wide audience, I will give a brief introduction about the neutron scattering, because I am by training the neutron scatter. So the thermal neutron, unlike to X-ray, they have the wavelength order of angstrom as well as the energy order of milli-electron volt. So by this we can do both the structure of the bilayer as well as the dynamics of bilayer. So structure tell us how the lipids are arranged in the membrane, and the dynamics tell us how they are moving within the membrane. This is the snapshot of our MD simulation. And for the stochastic motion, we do quasi-elastic neutron scattering. We call it quasi-elastic because we are centered at the elastic, but we mainly interested about the broadening of the elastic peak. And this broadening is inversely proportional to time scale of the motion. So by this technique, we can qualitatively and quantitatively both can estimate the time scale as well as the geometry, how this motion is diffusing, and what is the potential barrier. All three kind of information we can get by the twins. And this is the Dhruva reactor, where we do have a different spectrometer and diffractometer for the structure as well as the dynamics. And this is the twins spectrometer we do have in the BARC. So for the young generation, we have written a very instructional type of article on the neutron scattering to explain all the structure and the dynamics aspect of the biomembrane. And we have covered all the very basic fundamentals of the details of the measurements and the data analysis part on the small angle, membrane diffraction, reflectivity to quasi-elastic and neutron spin echo. And we have recently written a very detailed review article on the membrane dynamics, where we cover all different kind of motions with current to update, how to observe, and so we are working on this area around last 1 decade, and here I will talk about how these antimicrobial peptides affect the membrane fluidity. This change in the membrane fluidity affect the stability of the cells, and they do also affect the structure. They do allow to the segregate of the lipids, so lateral segregation of lipids. They also do the membrane softening. And to use the antimicrobial peptides, they should selectively act on the bacterial membrane, not on the mammalian membrane. So we also investigated the selectivity of the antimicrobial peptides, and if time permits, I will talk about some antimicrobial other agents like ionic lipids. So we have taken a system, zwitter ionic lipids, it's a DMPC, and the malatin, it's a B venom, it's a 26 amino acids. And Huang explained the action mechanism of this malatin peptides with this lipid membrane. They say at low concentration of the peptides, they are typically in acid states. Acid states, they mean about the surface, the peptides on the surface, and they do membrane perturbation. But when we increase the concentration up to critical concentration, then they change their orientation and they create the pore, and this is the traditional action mechanism by which this peptide kills the membrane. But what we found at low peptide concentration, though there are no stable pores, but they show the bactericidal activity. So what is the action mechanism? So this result clearly indicates the pore formation is not the only mechanism by which they kill the cells. So we prepare a unilamellar vesicles of DMPC using extrusion, and it's a monodispersive, and then we have carried out the in-plane neutron diffraction and the oriented circular dichorism just to confirm at this low concentration there is no stable pores. Then this low concentration do peptides interact with the lipid membrane? We have done the circular dichorism and we found, yeah, initially in the solution they are random coil, but when they interact with the lipid membrane they form a beautiful alpha helical structure. What do they affect on the bilayer? So we did the small angle neutron scattering and we see with the temperature bilayer get thinner, but when you add the malatin at the order phase, the phase transition around 297. So in the order phase we do see a membrane thinning, but in the fluid phase we don't see much significant effect. So we carried out Newton elastic intensity scan. It's a beautiful measurement. It's very simple, like you can understand, like a calorimetry. But in the calorimetry, we do see, we can talk about the phase transition by looking the peak enthalpy. But it's difficult to tell by this calorimetry that this phase transition corresponds to the structural or the dynamical. But Newton elastic intensity scan, it's a very similar. You measure the pure elastic intensity with the varying the temperature, but it can distinguish between the structural transition and the dynamical transition. What I mean to say, the dynamical transition, if a transition happens and then the change in the dynamics of the system. So here, like at the calorimetry we talk about, we show a very small hump. It's a pre-transition where the membrane go from gel to ripple phase, and then it's a main phase transition where the membrane go from the ripple to the fluid phase. If you carry out the elastic intensity scan, it's monotonously decreased with the temperature. It's like, because you're increasing the temperature, more quasi-elastic, more dynamic. But you see a small kink around the corresponding to pre-transition and a large jump, a large drop at the main transition. So the elastic intensity measurement suggests that at these transitions the membrane dynamics also significantly affected. They are the corresponding to dynamical transitions. But what's the most surprising, if you add the malatin, a very small amount of malatin eliminates both the pre-transition as well as the main transitions. And if you do the carefully measurements, if you normalize the elastic intensity, it gives you more information. So this small amount of peptides not only affect the phase behavior, but what it do in the order phase the elastic intensity is lower, but in the fluid phase the elastic intensity is higher. So what it suggests, in the order phase this peptide create disorder in the membrane, but in the fluid phase they create like a stiffening agents. So they show a contrasting effect depending on the phase of the membrane. To investigate this, we have done the Quantz measurements, and as I mentioned earlier, the time scale of the motion is inversely proportional to the broadening. So by qualitatively, if you look at the broadening, we see that in the order phase, if you add the malatin, it will become more broader. But if you add in the fluid phase, the broadening become lower. So we do a detailed analysis of this modeling, and we found two distinct motion of the lipid bilayer. One is this like a lateral diffusion, and one is the internal motion. And if you see the Q dependence of the lateral diffusion, the HWHM of the Lorentzian, we found it follow a beautiful Fickian law. So by the slope you can estimate the diffusion coefficient of this lipid bilayer, and what we found very beautiful results, that in the order phase if you add the malatin, it acts as a plasticizer, it enhances the lateral diffusion, but in the fluid phase it affects the dynamics and it reduces the dynamics significantly. So I already mentioned the dynamics mainly control the fluidity of the cell membrane, and if you it's a very important characteristic of the living cell, and any subtle change in the dynamics of the lipid membrane affect the fluidity. So we propose a new action mechanism of antimicrobial peptides, which say that these peptides need not to be a high concentration. Even at a small concentration they affect the phase behavior as well as they affect the dynamics, so they affect the fluidity of the membrane by which they can kill the cells. We choose another peptide which we know it doesn't form the pores up to very high concentration, so we can talk about the concentration dependence. And what we found in gel phase, not significant, but in the fluid phase, yes, it again affects the dynamics very significantly. And if you increase the concentration of peptides, it's a monotonously decrease up to here. So yes, this is the action mechanism, but do the effect on the membrane dynamics have any indirect effect on the structure? Because we know the cell membrane is not the single lipid system, it's a very heterogeneous mixture of the various lipids and other things. So what we have created a beautiful experiment, we have taken the two different lipids, a DMPC and DMPG. Because neutron we can play the contrast, so we have deuterated the tail lipids, and this is the anionic and this is the deuterionic, and we make a very homogeneous mixture of the lipid system. And what we did, we play with the DTO, with the contrast, and we found that this contrast we don't see any scattering. So like if you see the pure membrane, you don't see any scattering on the, but when you add this very small amount of peptides, what you do, they disturb the homogeneous mixture of the lipid membrane, and they create that the similar like anionic lipids, they come together and create lateral segregation, because they are deuterated one and they are non-deuterated one, so they create nano domain, and by this nano domain you see some rise in the scattering intensity at the low Q. It's more clear in the difference. So, but this creation of nano domains because of the effect of the membrane dynamics or not. So we did one more experiment. What we did, we took the lipids, just reduce the temperature below the phase transition temperature where we know the dynamic is affected. So in that only pure lipid, if you see without peptide, we still see some kind of a formation of the nano domain. So because the lipid dynamics is restricted by this peptides, they confirm that because of the affecting of the membrane dynamics, you can see the direct formation of the nano domain, which we call lateral segregation, and this is the first time we directly observed by the experiments, and this was highlighted on the cover page of the Langmuir. We do have also carried out the spin echo measurements at different length scale and the time scale, and in the spin echo measurements we are looking the whole bilayer. If you see the Q range is very low, like a small angle, we are going at very low Q value, and we are looking the intermediate scattering function is nothing like a SQ, inverse Fourier transform of the SQ omega, and we use the Jolmal-Jannat theory to describe the data. And what we found, if you increase the malatin, the membrane become more softer. The bending modulus of the membrane decreases. So by this, it show a very contrasting effect. Like if you add the malatin, it reduces the lateral motion, but it also affects the bending motion. We also done the one more like this PRL. They show you should see one more interesting another dynamical behavior which we call the thickness fluctuations. If you contrast match correctly, and then you see the only head group motion. We repeated this experiment and we found if yes there is an additional motion of the thickness fluctuation, and then we add the malatin and we found it do affect the thickness fluctuation of the membrane. So we have proposed like many different actions of antimicrobial peptides. They affect the membrane dynamics, they make membrane softer, they do lateral segregation. But to use for the antibiotic or the use and the like a diagnostic probe, like an infection imaging probe, they should selectively act on the bacterial membrane, not on the mammalian membrane. And we do have like these membranes have difference in the composition. The bacterial cells doesn't have the cholesterol and they most have the anionic lipids. So we choose a two model system like with and without cholesterol, and what we found, if you add the cholesterol in the system, the effect of the malatin they mitigate. So the destabilizing effect of malatin can be mitigated in the presence of the cholesterol. So we show by this measurement that they selectively act on the bacterial membrane. Another measurements we have carried out because this peptide is very useful for the infection imaging probe. It's a very upgoing interest if you want to distinguish between the sterile inflammations and the antibiotic bacterial infection, because both have the different treatment. So we have mimicked the two different model system for the bacterial and the mammalian, and we carried out measurements with the UBI peptides by different like CD, light scattering, and the isothermal titration calorimetry. And what does say, these peptides selectively act on this deuterionic POPC model mammalian, on the model bacterial membrane, not on the model mammalian membrane. And then we have carried out the quench measurements, and we see that in the dynamics they significantly affect on the bacterial membrane. But we need to improve the pharmacokinetics because this peptide is very big, 1 to 59. So we have choose the UBI derived peptides to improve the pharmacokinetics and repeated the similar measurements, and the results say that 2941, it's slightly longer one, has the better affinity towards the bacterial membrane, and we did the light scattering and the quench, and it show. And these peptides we collaborate with the Dr. Mukherjee group for the radiopharmaceutical, and they have made a probe for the infection imaging probe, and they have carried out the human positron emission tomography using this probe, and it clearly shows that these peptides can be used for the spinal TB infection as well as the thigh infections. So this is the another antimicrobial, but with the time I limit this part, and this I conclude here that the new action mechanism of antimicrobial peptides, they affecting the phage behavior as well as the lateral segregation, make membrane softer. They selectively act on the model bacterial membrane. These peptides can be used as the infection imaging probes, and other antimicrobials suggest the interaction with the membrane play vital role on the action mechanism. So I would like to acknowledge all my collaborators, Dr. Mukherjee and my group, and Sajal from the Shivnadar University, the ionic liquid growth, and my collaborator from abroad. And thank you very much for your kind attention.
Thank you, Dr. Sharma. Quick question. Yeah, Raja.
No. So yeah, no spin. So I use in the occasion NIST, USC. Yeah, Grenoble we have.
I have one quick question. You know, when you get a bee sting, you get a pain. How does that get reflected in the membrane structure?
So the pain, so we have done some work on the like a pain reliever also, like aspirin, ibuprofen, and the pain kind of mechanism is we call the COX mechanism. There's the COX enzyme there, and it's the prostaglandin. This is like a messenger. So when you pinch something, you have a pain. This COX enzyme generates the prostaglandin, and this is like a chemical messenger which
It's
gives
kind
you
of a piezo effect.
so what we found that they do have some correlation with the membrane structure and dynamics, but no direct evidence in the real.
Thank you.